Hello. So today I will be discussing on ultrasound beamforming. Okay, we'll be discussing ultrasound beamforming. It is an important topic on how do we construct images in ultrasound because it may seem to you that it is pretty easy after getting the reflections to form the image, but the process is not so simple, and it is quite involved in terms of how to extract the images once you have the radio frequency received at multiple at the transducers. Now typical medical ultrasound transducers are multi-element transducers. So every transducer will have multiple elements in it, and what we can do is we fire these ultrasound elements. We fire these ultrasound elements by say exciting these with square pulses. Each of these we excite it with a square pulse. We can excite all of them together with the same type of square pulse. Then what will happen is, depending on the transfer function, electrical to mechanical transfer function of each of these transducer, what will happen, it will lead to, so we try to excite it with almost like an impulse. This voltage is almost like an impulse. So what will go get at the output of the transducer will be impulse response of the transducer, very close to which are typically very close to a Gaussian modulated sine wave. Okay, so the sharper this impulse response of a transducer is, each of these transducers have an impulse response. So if a transducer has an impulse response which is something like this, versus a transducer which has an impulse response which is just like this. Impulse means if I give the transducer a single sharp voltage um, input, then what is the output it gives? Suppose this is it's a single input transducer, and I give a very sharp single voltage strike to it at the input, then what is the output it gives? So this is called as the impulse response. The transducer which has a sharper impulse response will give us a more sharper will help us to reconstruct very sharp images. Okay, versus transducers which have less sharp impulse responses. So what you can do is you can excite all of these transducers at the same time. If you excite all of these transducers at the same time, then a impulse response starts from all of these transducers at the same time. Okay, and when the impulse response starts from each of these locations at the same time, then you will have a so there is, as we have discussed, there is a near field, and then there is a far field for every transducer. So every transducer has a near field far field transmission, near field far field transition. Now in the near field, the field is quite jittery, and it is difficult to know exact field intensity at any point within the near field. But in the far field, we can assume that the transmission is almost like plane waves. Okay, so the transmission in the far field is almost like plane waves. So in the reconstruction process which I'll be discussing, or the beamforming process which I'll be discussing, it will be only valid in the far field of these transducers. You can do the near field far field calculation based on the third lecture of the ultrasound series which I had done last in the last lecture. So if a object is in the far field, then to that object, if all these transducers are fired together, then the beams from all these transducers after the near field far field transition, after in the far field, will appear almost like parallel plane waves. Okay, in the far field, if there is object, if this is the object in the far field, and these are the ultrasound signals, then they hit this object, and once they hit this object is excited. All the points on this object would be excited, and each point in this object will start behaving like a radiator itself. Okay, So what will happen is once this object is insonated with ultrasound, each point on this object will start radiating spherical spherical sound waves, which will come back to these transducers. Spherical sound wave means each of these points will start radiating sound waves, which will start coming towards the all our transducers. So every point here will become a spherical radiator, every point on this object, depending on what's the intensity which hits it. So every point on it will become a spherical radiator. So the each of these transducers will receive the sound waves which are radiated from each of the points on this object. Okay, so let's take a simple case. For example, suppose this is suppose we have about 6 or 7 elements here of transducer, and suppose this is the object which is in the far field, a single point in the far field. It's just a single point, not object. So suppose there is a single point in the far field. Now after the object has been hit by ultrasound, the object itself becomes a spherical radiator, and it's so suppose each of these transducers, so these transducers had an impulse response which is like this. Then this all of these in the far field would travel and hit this point, and after that this point will start reflecting a very closely related shape, which is also a Gaussian modulated sine wave, and it will radiate it as a spherical wave. So this spherical wave will propagate from this point. Okay, and the shape of these waves which are transmitted from this place are also Gaussian modulated sine wave. Now let's assume that a single Gaussian modulated sine wave is traveling from this point. Then what will happen is this wave will travel from this point to this point. Okay, so for the onward transmission, that is from the transducer to the object, we can assume that as if a single what to say as if a single plane wave was transmitted in the forward path. Okay, so the total path from this point to this point is, say, from the transducer till the object is it the distance is about distance is, say, d. Okay, now to the center, suppose this is the central transducer, a central transducer, then till the central transducer the distance is d. Okay, but to the peripheral transducers the distance can be different depending on where the transducer is. Depending on where the transducer is located, you will have a different distance. Okay, and these distances can be calculated. Okay, and these distances are calculated, which is simply, if you know the this is suppose you know this is known as the distance between the transducers. Suppose this is k, then you know that k, this will be square root of k square plus d square. This will be square root of 2k square plus d square. This will be square root of 3k square plus d square. Okay, so total time for the time of flight from the transducer till it comes back to the transducers, okay, can be assumed like in the forward path all the transducers have a path length which is d, but in the backward path all transducers have a different path length. For example, this transducer will have a total path length of travel, total time of flight from this point till this to the point of observation. The forward path will be taken as d, and the backward path will be taken as square root of k square plus d square. Okay, so this is the total path. Okay, so once we fire the transducer, and after that what we do is so suppose this is that transducer. So once we fire the transducer, so a wave starts traveling. It hits the point of observation. Say it hits the point of observation, and then um, it's a little difficult to explain, because when in the forward path we assume that it's a plane wave which is traveling from the transducer face itself. Okay, so all the transducers we assume that have the same path length from in the forward path, but while coming back we are calculating we are calculating the time of flight of the wave which originated from the point of observation. Okay, not from the transducer, so that path length becomes different. So total path length which but the once we fire the transducer, once the transducer is fired, after that immediately sampling starts. Okay, sampling starts. So sampling will start, but the signal will arrive back to the transducer only after traveling this much time. Okay, this much space, which can be converted into the time by looking at what is the speed of sound. Suppose this is speed of sound, vs, then total time taken by the sound wave to travel from the transducer to the point, and then from the point back to the transducer, will be given by d plus square root of k square plus d square by the time of by uh, so this is the speed of sound. So suppose this is the time which it takes, time of flight. Time of flight will be given by speed of the distance divided by speed of sound. Okay, which can be different in different material, and that will give you the time of flight. So immediately after firing the transducer, we start sampling, and so the sampling will give us the waveform which it receives from the point of observation at a distance or at a time, because this is sampling time. So this time of flight for this transducer will be given by this formula here. Okay, and this time of flight can be calculated for different transducer, for all these transducers. Okay, so it is so every transducer will receive a signal from the point of observation. Okay, and we can so the idea is, can we find out the location on the radio frequency wave? um, how do I explain? The way we explain it is, we excite all of these transducers together, and once we excite all these transducers together, all of these transducers will have a Gaussian model sine wave which will travel at the same time, will start at the same time. Okay, but while coming back, and after that we start to sample. Once we start sampling, the first transducer will receive uh, which transducer will receive the signal first? It will be this transducer, because this distance is the shortest from this point to this point. So this transducer will receive the signal first. So um, if these are our, say, 5 transducers, so this will receive our signal first. After that, this will receive, so that means it will be farther away in time. So this is your time axis, and after that this will receive, so this will be farther away in time. After this and this will receive the signal together, so this will be together with this, and this will receive together. So this and this will receive signal together. So if what you can see is, even though there was a single point, when it arrives at all the transducers, at our observation transducers, they arrive as, at different time points. Okay, so a single point is showing up as a bow kind of signal. Okay, and if you have 2 points, then you will have 2 bows. Okay, if you have 2 points, say, instead of this single point, if you have 2 points, then what you will receive is kind of 2 bows, one here, one signal here, and the signal here. So if you have multiple points, or there is a complex object in the field, then the radio frequency which you will receive will be pretty complex. And the aim is to come up with a method, or aim is to combine all these signals so as to reconstruct this bow type of signal into a single point. Okay, and how do you do it is, let's just consider a single point, the output from a single point, which will be, so this is the output from a single point for our 5 transducers. Then what we do is, we take the first point. It is no. What you do is, suppose you want to reconstruct. First, you have to tell your you have to make a program which will be told to reconstruct a particular zone at a particular distance from the transducer field. Okay, so for each of these points, we don't know where the objects are. So what we do is we assume there is a point with some value in the space. Then we try to reconstruct the amplitude of this point. How do we reconstruct the amplitude of this point? We first find out what is the time of flight which it will take for this point. If there is a point in this space, how much time will a sound wave from the transducer take for a sound wave to go from the transducer to the object and then back from the object to each of these elements? Okay, and so once we fire, what we have is we have a signal, we have a series of signals, series of radio frequency waves for each transducer, some kind of radio frequency waves which are there for each transducer. We don't know what is the object which, or what kind of objects created this radio frequency waves. Then assuming so suppose you are trying to reconstruct this pixel and the total time of flight which you calculated is say t1 for the first transducer, t2 for the second transducer, t3 for the third transducer, t4 for the third transducer, and t5 for the fifth transducer. Then you, for the first transducer, you have the radio frequency wave. You go till the point t1 and extract the amplitude there. Okay, so store it as a1. Then go till time t2 for the second transducer, and suppose you extracted the amplitude as a2. Okay, this amplitude a2. Third one, suppose you extracted from time t3, you extracted amplitude a3, a4, a5. Then these five amplitudes you add. Okay, you summation of all these five amplitudes, and then whatever amplitude you got, you put that value here at this pixel value. Okay, you repeat it for every pixel value in the zone in which you want to do the reconstruction. Okay, so you can choose what is the granularity, like what is the pixel distance between each pixel, and what is the millimeter, suppose x1 to x2, and say sorry, this region which is typically called z dimension, and this dimension we are calling x dimension. So you can reconstruct, this is called the z dimension, so z1 to z2 and x1, suppose x1 to x2, x1 to x2, with a granularity which you can choose, like what is the pixel difference or how many millimeters difference are there between the pixels. And then for each point you can reconstruct the pixel values, and once you reconstruct the pixel values for each point, you can basically form this image and then show this image to the user. Now reconstructing this image of course means that you have to go through the RF signals for each transducer, find the amplitude locations for each, and then add them up and then fix that amplitude value there. So depending on what is the granularity, like what is the difference between each pixel and what is the distance or what is the overall zone you want to construct, the time required for reconstructing each image will be more or less. So if you want to reconstruct images faster, then you should choose a smaller distance and you should have farther distances between the pixel values, pixel locations. Okay, uh, on x and y dimension. So depending on how closely or how sharply you want to reconstruct the images, you can choose these dimensionalities and these locations. So you initially you get a bunch of radio frequencies, then you use the radio frequencies to reconstruct your images. Okay, so that's the overall idea of how do we do ultrasound image reconstruction. There is a software called field 2, okay, which runs on MATLAB. You can download it from here. It's a simulation software for ultrasound, field 2 simulation program. Its link is given here, field2.dk, and it you can download this Windows version from here, and then it runs over MATLAB as a plugin. So you download it into one of your directories, So one of your directories, for example, here I have downloaded to desktop in MATLAB. uh, I think so. Let me check. All right, so I have a software field 2. I have created a field 2 folder in the desktop. In that, I have put this software. This software is basically a folder. You will, once you extract, it will be a folder. In the folder, you have all these functions which you don't have to think about too much. These are all programmed, and they will help you to reconstruct, or sorry, they will help you to form images or simulated radio frequency signals. The user guide of how to use the program and how to call the functions are here in this file, users underscore guide.pdf, which you will be able to get from that folder. So this folder, once you download, you go to that folder in your MATLAB, and then you can add it to path by just let me add my let me put my keyboard. So you can add it to your path by putting right clicking here, and it is here you can add from path, add to path. Right now it is already added to my path, but you can use this link here to add it to your path. And then in this software there are different functions which you can use to simulate linear arrays. So there is a function called XDC. So let's go to the user guide of uh, this software. So here there are, this user guide basically gives you a lot of information um, how to make how to make use of this software. uh, but this is all command line. It runs from MATLAB. So you have to have MATLAB first, and right now it is running with MATLAB version 2018b. Through IIT Roper's through IT Report, you will get the access to MATLAB, and you can download this particular version. You can use the academic license of IT Report to get access to this particular version. You may also try with other version. I have not tried with other versions, but it works. Okay, it's right. It works well with this version for me. If it doesn't work with other versions or more latest versions, then you might have to look at using this version. So in this I will post this function, these couple of functions. um, Basically I'm using two function. I have made two functions. one is a One is a form image function which uses that same logic which I had given, which I had explained right now in this notebook. And So this function uses this logic to form an image given a RF array is given to it. So that RF array, that radio frequency array, can be created by using a function which is XDC underscore linear array, where you give the number of elements, element width, element height, the difference between each element of the transducer. These are all transducer elements. What do I mean by transducer is I have used a Philips transducers. So this L7 array.mat, which is here, this creates this trans function. If you go to this trans function, so here you can see this basically defines a transducer, a Philips transducer, which is the L74 transducer. This transducer was available off the market. I had used this transducer earlier in my research. So this is the Philips transducer, ultrasound, medical ultrasound transducer. In this, there are 128 elements, and those 128 elements are those one. So you can see here the number of elements are 128. The element, its center frequency is 5 megahertz, and everything else is defined in terms of its wavelength. So center frequency is 5 megahertz, means wavelength is um, wavelength. If you take say 1540 meters per second is your sound traveling speed, then your wavelength can be calculated which is given by the 0.308 micrometers, I believe. Sorry, 0.308 millimeters. So this is the wavelength of which is created from a 5 megahertz transducer running at 1540 meters per second sound speed. 1540 meters per second is the speed of sound in tissue, not in air. So it's a little complicated to understand everything in this code, um, but I want to just give you an overview of how it is used, and I will give you maybe one assignment of just running this code and creating few more points than what I have done, so that you yourself understand how to, at least the basic process of how to use it. So here the number of elements are 128, element width is 0.187 into wavelength, which is 0. So element spacing is 0.9675 into wavelength. So everything is defined in terms of wavelengths. Element positions, like this has the center element. So there are 61, there are 128 elements. So, and it varies. So you can see there are total 128 elements, and it varies from minus 61 wavelengths to plus 61 wavelengths. Okay, with a difference of with a difference which is given by um, spacing. Okay, 0.9675 wavelength. So what I mean by this is you have so the transducer is like this. It has, so this has 128 transducer elements. From one element to the next element, the difference is 0.9 lambda, that is 0.9 wavelength. And this center, the center transducer in this, so if this is the center transducer, the center transducer is sitting at 0 wavelengths, and from this point to this point is sitting at minus, sorry, 0.9 wavelengths. This point to this point is minus 0.9 wavelengths. This one is minus 1.8 wavelengths. Like this, if you go, it is minus 60 wavelengths, and this is plus 60 wavelengths type of this is the arrangement of transducers. And using this, you can calculate the absolute location, so of everything in this space, and so if you go through this function, single point test, in this I have first created some of the initial variables which specifies the number of elements, the transducer frequency, which is 5 megahertz, sampling frequency, which is the once the, what is sampling frequency? Sampling frequency, what I mean is, uh, this is your transducer frequency, which is say 5 megahertz. 5 megahertz means this point to this point is 2 uh, 0.2 microseconds. Okay, now this is the analog wavelength, analog waveform. But when we sample it, the sampling has to be done at a particular rate, because digital sampling rate, it is done at 100 megasamples per second in the hardware, which I have defined. You can use at different megasamples per second, but 100 megasamples per second is defined in this code, that the sampling rate is 100 megasamples per second. The speed of sound is 1540 meters per second. Wavelength is calculated by speed of sound divided by center frequency, and multiplied by 10 to the power 3 to give it in millimeters. Then I loaded the L74.mat, which gives me this trans variable. In it there are definitions of the distances between the elements, and I calculate the element width, element height from the trans variable. Inside the trans structure, actually there are these definitions of element width, element height. Actually I'm keeping as same as element width, and Carfax is the distance between the two transducers, the gap between the two transducers, not from center to center, but just the gap. The We want to focus the transducers, which is physical focus the transducer, which I'll not discuss here. The physical focus the transducer is very far away in the field. Then we enable all the elements. We create the receive aperture, which is how the final transducer will look like. So it will have 128 elements. Each element will have a height, width, and it will have a difference between the what is the distance between each element and where is the focus. So these are all defined in this. So this creates the transducer receive and receive aperture, and we use the same aperture for transmission and reception. We can use different. For example, what I'm saying is the same transducer. So you first define that there are 128 elements, which each element having a particular width and particular height, and the difference between these two is defined by curve underscore x. Okay, so this defines your transducer shape. Okay, and we are also telling that the same transducer will be used for transmission as well as reception. In field 2 we can also define two transducer arrays. We can define that one transducer array will be used for transmission and the other will be used for reception. But in this case, we are using the same transducer array for both transmission and reception. Okay, so then after that we give us a Gaussian model sine wave. We create a Gaussian model sine wave, which is uh, by using a Hanning window over a sinusoid. It gives us we create an impulse response and assign the impulse response to each of the transducer elements. Okay, so uh, every transducer element is assigned a Gaussian modulated sine wave as its impulse response. Okay, and once we do that, then yeah, we assign the impulse response to both the transmission and the reception aperture. This XDC underscore excitation is used to create the excitation. We excite the transducer, uh, emit aperture. Sorry. So how are you going to excite this transducer? We are giving one impulse. So this is basically that you are going to excite the transducer with a single impulse. After that, you can specify what are the points in the space. So you can specify here. I've specified one point. So in this space is defined. This space is defined with respect to the central transducer actually. So if you have this as your transducer body, so this is the point which is 0 0 0, or in this case which is this point is in x direction. So this is your x direction, this is your z direction. Okay, so this is x y z. So we are saying that this transducer is the center of this universe. With respect to this, now we are placing points. One point is placed 25 millimeters away from the transducer. Uh, so one point is placed 24 millimeters away from transducer. So this should be actually, sorry, not this one. One point is placed 24 millimeters away from the transducer and other is placed 25 millimeters away from transducer, but the second point is 1 millimeter to the right as well. Okay, to the bottom as well. So what is saying is we have 2 points in the space which are looking like one is exactly 25 millimeter in the central space, 25 millimeters, and the other point is to the right a little bit. uh, Sorry, the other point is, sorry, one is 24 millimeter, this is 24 millimeter, other one is at 25 millimeters but little bit to the right, 1 millimeter down to the bottom side. So that's the definition which you have given here through this function point position. After that we calculate the scatter we calculate the RF data which will be received by all these transducers by using this function here. Okay, so this definition of this function you can again get from the user manual here. Okay, you try to search this user manual for that function and you will get the definition and go through that function, how this function is used. This will return to you the radio frequency data and the start time where the radio frequency actually non-zero values of radio frequency data start. Okay, so because what do I mean by non-zero values? Because suppose this is a point, this transducer will only start receiving this transducer will receive the signal first. So the time it will take, so once this transducer is excited, a signal will start traveling, it will hit this point, and then this point will get excited and it will start radiating, and this will come here. So what you'll get is a bow shaped signal for all that. Means for this transducer you'll get a signal here, for this it will get a signal here, in times domain. So before the for this you'll get here, for this you'll get here. Okay, but before this time period every other transducer has zero amplitude. No transducer is getting any signal before this time. Okay, so that's why we only record signal, or this field 2 only shows a signal from the start time onwards. Okay, so the RF which is shown to you is only from this point onwards, and and it additionally returns to a start time so as to save space. It doesn't want to fill RAM by data which it anyways knows is all zero. So it gives you this start time value, so you can add this start time to all your calculations in order to find out where the signal is coming. Okay, so that's what it does here. So you get a scatter. So if I run this till this point, say I put a breakpoint here and then start running it. So you can see we got these two. Let's start. So if you go through these figures, this figure is not necessary. So this is your transducer array, which is defined by So this is your transducer array, which was defined by us. Okay, so each of these elements is having a certain width and height, and there are total 128 such elements. Okay, so there are total 128 such elements. So this defines your transmit and receive aperture, and it is displayed here. After that, each of these element have been assigned a impulse response which is like this. So okay, so this is the Gaussian model sine wave which has been assigned as an impulse response to each of these transducers. After that, when all of these transducers are fired together, then the signal which is received by each of these transducers so is given by this. So you can see on this axis there are 128 elements. So and on this axis is the RF data for each 128 element. Okay, so let me rotate it. Okay, so you can see although there are just 2 points which were simulated, the transducer is sitting on this side. Okay, transducer is sitting on this side. This is only showing value from the start point onwards. So the first point is somewhere here, the second point is somewhere here, and this point is about 25 millimeters, 24 millimeters away from the transducer. And because of that, you see these do not look like single points, they look like complete bow waveform. So there needs to be a reconstruction algorithm in order to finally make an image. These are non-beam formed images or signals. So you have to beamform. Beamforming means following the process which I had. Beamforming means following this process. Okay, following this process outlined here, and that is what this function is doing. Okay, where you pass the radio frequency array, you pass the element position, x position, sound, speed of sound, RF start time, sampling frequency, image, x range and y range in which you want to reconstruct. X range, y range means uh, this range. Okay, this is the x range and this is the z range. You need to pass x range and z range with the granularity which you want in the image, and that is what has been uh, sorry. So in this, if you see x in micrometers range, So it is reconstructing from minus 20 millimeters to 20 millimeters. It is given in micrometers here, that's why I multiplied with 1000. And z range, sorry, this is x range. X range is minus 2 millimeters to 2 millimeters, it is reconstructing. And z range, it is reconstructing from 24 to 32 millimeters. Okay, so we can actually change it a little bit earlier than this 24 point, because we are trying to look at these 2 points which are located at 24 millimeters and 25 millimeters away. So we need to reconstruct a little bit earlier than that. So say 23 millimeters to 32 millimeters we reconstruct. uh, and then we can call this function which I had written. I strongly recommend that you go through this function and try to understand how this really implements the same logic as was explained here. Okay, for each element. And then this reconstructs all the RF lines to form a single image. Okay, now that single image is stored in I. So if I go forward with this, and then finally the same image is shown, but the final image will have a Ripley effect, because it comes out, every point comes out almost like, you know, it doesn't come out uh, every point comes out something like this. So suppose this is the image you're looking trying to reconstruct. Instead of a single Gaussian type of output for a single point, it might come out like this. So you need to detect the envelope of the signal which is received. So that's what we are doing. We are trying to we add a envelope detection before showing the image here. Okay, so if I continue with this, X range and X range was defined between -1 and -2 and 2, and in micrometers, -2 millimeters and 2 millimeters. It was defined in micrometers, but in this range. Z range again was taken from 23 millimeters to 32 millimeters to cover these 2 points which were defined by us earlier. And then we do a we try to show these two this image by detecting the envelope of this signal. And then the final image, the way it looks on here. So you can see the 2 points are reconstructed, and they will have these wingy appearances. There are different ways of reducing these wings, but these wings cannot be completely eliminated. These are because of side lobes which occur in these transducers. And so you can see the first point is reconstructed around 24 millimeters, and second around 25 millimeters, and 1 millimeter in the x direction, and this one is exactly at the center in the x direction. So this is how we reconstruct. I don't have enough time in this to really go through very detailed explanation of this code, and I believe if you put enough effort you will be able to understand based on the explanation which I have given you here. Okay, so this is how we do reconstruction of ultrasound, means RF to image, and it's an important process to understand for any ultrasound engineer. And yeah, so that's it I want to discuss today. Thank you for listening.